In this video, we are going to talk about vector fields. And what they are basically a bunch of vectors. And in general, a vector field is a function whose domain is a set of points in R2 or R3, and whose range is a set of vectors in R2 or R3. So let me write definition. A vector field is a function. We usually write the function of the vector field by capital F with an arrow that assigns to each point in its domain a vector. Okay, we can define vector fields in a plane or in a space. So in the plane, we usually write the vector fields by F, and since the vector field is in the plane, so it needs to have two coordinates. So I'm gonna have something times I plus something times j, and the coefficients would be p and q, where p and q are both functions of x and y. Okay, and so since our vector field here is in the plane, at each point x, y in the plane, we have a vector f of x and y, which could be, let me basically write this one in here, a vector with the first coordinate p of x and y and second coordinate q of x and y. Great. Let's look at some examples. Example 1. Let's look at the velocity field. Velocity field. And what is that? Something like V, capital V, which is a vector field on x and y. It's wind velocity that gives you a vector at the point x and y. Okay? For example, it could be something like this. 2I plus j. Okay? This could be a velocity vector field. Oops, let me write this as v, with the constant velocity at every point. Let me graph this vector field. This is a vector field in R2. Okay, since we have two coordinates in here. The first coordinate is 2, the second coordinate is 1. Okay, 2 and 1. So it's a vector field in R2. At every point, basically, we have the constant vector 2 and 1. For example, at the origin, we have the vector 2 and 1. This vector. Okay, at another point, for example, at the point 3, 3, we have the vector 2 and 1. Okay, at the point, for example, 0 and 2, okay, we have the vector 2 and 1. And if I want to graph this vector field, I should have something like this. I'm gonna graph the vector 2 and 1, so this is not scaled, okay, at every point. You see? At every single point, I have the constant vector 2 and 1. So this is the graph of a vector field. We can continue graphing this vector field at every point. Or look at another example, example 2. We can have the vector field xi plus yj. You see, the coefficients were two functions of x and y. This time, these are the function x and the function y. Okay, let me try to graph this vector field. This is also a vector field in R2. And if I want to graph it, I need to plug in the points into that vector field. This is x coordinate, and then this is y coordinate. If I plug in the point 0, 0, the point 0, 0, the x coordinate would be 0, y coordinate would be 0, so I get the vector 0, 0, nothing. For example, at another point, at the point 1 and 0, when I plug it into here, I get the vector 1 and then 0. So it will look like something like this. 1 and 0, the vector 1 and 0. At another point, for example, at the point 1, 1, here, I have the vector 1, 1. Okay, let's have it in another point. For example, at the point -1 and 0, I get the vector -1 and 0, which would look like this. At another point, for example, at the point -1, -1, I have the vector -1, -1. Okay, let's go to another point. For example, here, this is the point 2 and -1. So I get the vector 2. I'm gonna move 2 units toward the positive x-axis and 1 unit down. Okay, and we can continue graphing this. For example, at the point 0, -1, I have this vector. Okay, at this point in here, which is 1 and -1, I get 1 and -1, something like that. And as you see that if I want to continue graphing this vector, it's gonna change the scale. It's gonna get bigger, right? Yeah, something like this. Okay, actually it needs to be in the correct direction. Okay, we can continue graphing this. Then let's look at another example. Example 3. Let's look at this vector field f, which is -yi plus xj. This vector would be -y and then x. And if I want to graph this, x and then y, and then at the point 0, 0, I still get 0, 0. Plug in another point, for example, 1 and 0. 1 and 0, the vector that I get would be 1. It would be 0 and 1, which is that vector. Okay, and the vector 1, 1, at the point 1, 1, I get -1 and 1. As you see, the vector field here, it moves. For example, at the point 0 and 2, when I plug it into here, I get 0 and -2. So it moves 2 times, 2 units toward the left. Something like this. For example, at this point in here, which is the point -1 and 1, okay, when I plug it into here, y is -1 and then x would be -1. So I get this vector, which looks like this. Okay, so basically this is a vector field that it gains a scale, okay, and it rotates counterclockwise. Okay, how about in a space? In a space, what do we have? Similarly, f, which is pi plus qj plus rk, where p, q, and r, these three are functions of x, y, and z. Okay, so in a space, you need to plug in the point in a space which has 3 coordinates, x, y, and z, into your vector function, and then you get a vector. Okay, if you do it for all the points, you get a vector field. Let's look at one example in here. For example, if f is 2I plus xyj plus 3x squared z k, this p, q, and r, these are functions of x, y, and z. And for example, at a point like 1, 2, -3, we get f of 1, 2, and -3, which is what? 2 is fixed. And then we get 1 times 2, which is 2j. And then we get 3, 1 is squared, 1 squared, and then z, which is -3, which is -6. We get the point, we get the vector 2, 2, and then -6. Okay, at every point in the space, we get a vector. Okay, one important vector field that we are gonna work on a lot would be the gradient vector field. So, gradient vector field. What is a gradient vector field? Is actually gradient of a function is actually a vector field. For example, for a function of 2 variables x and y, gradient of f is partial derivative with respect to x and partial derivative with respect to y is a vector field in the plane. And for a function of 3 variables, x, y, and z, gradient of f, which is partial derivative of f with respect to x, partial derivative with respect to y, and partial derivative with respect to z, is a vector field in a space. Okay. For example, if we have a simple function x, y, which of x, y, and z, let's look at a function of 3 variables, for example, x squared y plus 1/2 zy plus xy, okay? Then the gradient vector field would be this. Partial derivative of this function with respect to x would be 2xy plus y. Partial derivative of the function with respect to y is x squared plus 1/2 z plus x. And partial derivative with respect to z would be 1/2 y. Okay, it's a vector field because if I plug in any points in the space into this vector function, I get a vector. That's why it's a vector field. Now, after studying gradient vector field, an important question comes to our mind is that can we identify any vector field as a gradient of a function? The question is this. Can we identify any vector field as gradient of f of some function? Which means that if I give you any vector field, can you find a function whose gradient is that vector field? Well, the answer is no. If we can find a function whose gradient is the vector field, then we say that the vector field is a conservative vector field. Okay? If the gradient vector field is if the vector field is gradient of a function for some function f, then we say that f is conservative vector field. And f is called potential function for a vector field. Okay, in the next video, we're going to talk more about conservative vector fields, but this is basically an introduction for conservative vector fields and the vector fields.